Hello and welcome back to Basic Topology, the video series where we use topological arguments to prove important results in analysis. And indeed, in today's part 13, we will tackle the proof of Urysohn's lemma. And there you will see that the idea for the proof is quite simple, but the technical details require some time. But before we start, as always, I want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget that you can download the PDF version with the link in the description. And then without further ado, let's immediately recall the statement of Urysohn's lemma. There we consider a special topological space X, which means it should be a locally compact Hausdorff space. And then inside it we fix an open set U, and inside U a compact set K. So the picture looks like that, and then we want to define a continuous function f on X. This means we have a mapping from the abstract topological space X into the real number line. More precisely, we only want to have values between 0 and 1, where the non-vanishing values lie completely in a compact set inside U. And in addition, on the compact set K, we only want to have the value 1. So this means if we look at the graph of the function f, we start at 0 somewhere in U and then we grow up to 1 until we are constant at the set K. So this is the whole picture and the statement of Urysohn's lemma. And now in order to prove it, we actually have to construct such a function f. And after I show you the idea of this construction, you might see that it is actually not so complicated. However, as already mentioned, for a correct proof we still have to fill in all the details. So we already know the function f should be constant to 1 on the set K. So this is not a problem at all, and then outside of the set somewhere we can set it to 0. And then in between we can just set some other constant values. This should be easy to define, we just go stepwise to the value 1. And then afterwards we could just increase the number of steps and make them finer. And then the idea is to simply continue this until we have a whole sequence of step functions. Therefore you might already see that in the limit process we actually get out a continuous function. So the crucial thing that we need here is that our topological space X has a property that makes these steps possible. And exactly this we have already discussed in part 12, namely every locally compact Hausdorff space has intermediate compact and open sets. So let's simply use that to define our first step function. So please recall the statement of part 12, which says if we have an open set U given, where a compact set K is included, we find two sets in between. More concretely, we find an open set A, where the closure is a compact set. And with that, we already have the compact support for our continuous function f in the end. This means everything interesting for the step functions should happen inside this new set A bar. And this is quite helpful because it's also a compact set like K. So in our simplified one-dimensional picture, you could say this is our compact set A bar, and inside we just find the compact set K. And now it's not a problem at all to define a function that is constant to 1 at K and 0 elsewhere. So at the boundary of K, the function will just jump. And there please don't forget that the boundary of K can be a really complicated set, but we will simplify this in the picture. For us it just matters that this new step function that we call f0 is well defined. And of course we can just write down the definition because we only have two cases anyway. 1 if x lies in K and 0 if x lies outside of K. So especially we have 0 if x lies in A bar but not in K. So if we only would consider the function defined on A bar, we would have the difference A bar with K. And since our A bar here defines the value 0, we put an index 0 to it. In other words, I want to make the notations consistent here, so we put indices for each set that defines a value for a step function. Therefore, it would also make sense to have a set A1 that defines the value 1. And this is quite easy to get because we just have to apply part 12 again to get the intermediate sets. So now we see we have a compact set A1 bar for the value 1 and a compact set A0 bar to define the value 0 outside of A1 bar. So now we redefine F0 like we want to have it. It's quite simple, we just say it's 1 if x lies in A1 bar, and the value is 0 if it does not lie in A1 bar but in A0 bar. So we just have a set difference here that is quite easy to read. And just to be clear, we also define it outside of the sets we consider here, such that we have a function defined on the whole space X. But obviously the important part is here on the top. We jump from the value 0 to the value 1. And now, as already explained above, we will just define more and more steps, so let's go to the next step function. So for example, we could add the value 1/2 in the middle, so let's apply our part 12 again, but now for these two sets. This means we find an open and a compact set in between, and let's call them A1/2. So our chain here is extended, but not at the ends, but in the middle. So in total, now we have 3 different values for our new step function. So maybe let's sketch it, and please never forget, we have the subset relations, so A0 bar is always the largest set, where all the other ones are included. And moreover, we will never change the value at A1 bar at all. But what happens is that outside we will raise the value to 1/2 for our new set A1/2. In other words, we just have a new step here at our new difference set. Very well, this defines our new step function that we call F1. And as you can see, the definition looks really similar to before. We just have to put A1/2 in as well. And in fact, with that you already have the whole idea, because we just want to add more and more steps with such a definition here. More concretely, to get finer in our graph, we will just double the steps all the time. Hence, for the next function F2, we have to add the values 1/4 and 3/4. Hence, we have to apply part 12 2 times, once here and once there. This means the whole chain will get larger and larger, and it will be harder to write it down completely. However, this might not be needed, because you might already see the whole idea for all the other steps as well. So let's quickly sketch the picture, and then let's write down the general case Fn. So here's the graph from before, and now we add a step at 3/4 here, and one with 1/4 there. So again, at a given point x, the value of the function only gets higher, not lower. But obviously at most points the function stays exactly at the same value. In fact, this is already a key insight, because in the end we want to do a limit process. But first I would say we are ready to formulate the general case, so the step function for every natural number n. And of course this also means that our chain of subsets here could be really long. In fact, the lowest value we would find here on the right hand side would be 1/2 to the power n. This makes sense because we want to double the non-zero values in each step. And since we want to have the same step size here, the next value in the chain should be 2/2 to the power n. And then it's quite clear the whole thing continues until we reach the last value before 1. Hence there in the numerator we find 2 to the power n minus 1. So this is our whole chain, and now it's also possible to write down the explicit definition of Fn. The only thing we have to do there is to distinguish the different cases, which means we can use an index k. This means we consider x that comes from the set ak, or more precisely where k is in the numerator of the index, but it should not be in the one before, so not in k plus 1. So with that we have described all the cases, and you see the value at this point is exactly k/2 to the power n. So there we have it. This is the general definition of Fn of x. So for every n, it's a well-defined step function that looks like that, and we also know if we increase n, the steps get smaller and smaller. And moreover, by construction, we immediately see that for every Fn, the 3 properties from above are definitely satisfied. This means first that all the values lie definitely between 0 and 1, and second that the support of f lies in a compact set that lies in U. And the third part is simply that at the compact set, we are equal to the constant 1. So all these properties are satisfied no matter which n we consider. So this is quite nice, but because we always have a step function, we can definitely not expect continuity here. Obviously, this is something we want to get in the limit n to infinity. And to calculate this limit process, we should first look what happens when we go from n to n plus 1. Actually, we already saw that in the examples above, but it's still good to write it down. So you see, if we have the index n, we have the step size 1 over 2 to the power n. And then if we go to n plus 1, we know that the step size gets smaller, factor 1/2. But we also know that the new steps are put on top of the old steps. So this is how the construction works, and we see we cannot increase the values by much. The maximal increase is exactly given by the new step size, which is 1 over 2 to the power n plus 1. So in summary, we get two important facts out here. First, we know the values are non-decreasing. So no matter which x we consider, fn plus 1 of x is always greater or equal than fn of x. And second, this maximal increase we could have is definitely bounded by the step size we have in the step n plus 1. And this is quite helpful because it's always a power of 2. And now I can tell you that we can immediately use part A here to conclude that the pointwise limit function definitely exists. This is quite clear because for every x we get a sequence in R which is monotonically increasing and bounded by above. This one we already know because all the values are bounded by 1 anyway. Therefore the limit here also has values between 0 and 1. So for every x, this defines a number f of x, and therefore our limit function f. And now since every fn satisfies the three properties for above, they also hold in the limit. This means we are almost done with our proof because we have our function f already, and we just have to show that this one is also a continuous function. And in fact, this one is not too hard because we already have the bound given by the step size. So the idea would be to write an estimate with the function f instead of fn plus 1. Therefore, let's first do it for an integer m that is larger than n. Hence, by the triangle inequality, we can put in all the intermediate integers. So first we go to m minus 1, then to m minus 2, and so on until we reach n. And I would say let's keep it short because we already know that each part here has a bound given by the first index. So the first one is 2 to the power m, then we have 2 to the power m minus 1, and so on until we reach n plus 1. So it's actually a nice geometric sum formula. You see this if we use a sum symbol where we have an index k involved. And then we just have 1/2 to the power k, where k goes from n plus 1 to m. And now obviously on both sides we can just form the limit m to infinity. So on the left hand side we have the difference f of x minus fn of x. And on the right hand side we have a nice infinite sum where we have the geometric sum formula for it. And this one is quite nice because we have 1/2 to the power n plus 1 divided by 1 minus 1/2 as well. And by putting that together we just get 1/2 to the power n. And this result we can use for the continuity because it tells us that the difference between f and fn can be made as small as we want. And most importantly, this bound does not depend on the x we choose. However, before we go into the technical proof, we should first recall what continuity at a given point actually means. So we will fix a point x0 from the domain x, and then we will write something down that is something like a generalized epsilon-delta continuity. In fact, the epsilon we can keep to describe neighborhoods because we still map into R with the function f. In other words, on the right we have our standard topology we know, but on the left hand side we have a general topology. This means the open set in X itself cannot be described by just giving a delta greater than 0. But still it works similar because we just say that we have an open neighborhood V of X0. And then we just apply our function f to this open set V. And then we want that we map this open neighborhood to a neighborhood of the value. And obviously this one is just an epsilon neighborhood, so we have f of x0 minus epsilon on the left and plus epsilon on the right hand side. And this is the common definition of continuity at a given point. No matter how small we choose this epsilon neighborhood, we can always find an open set that maps completely inside this epsilon neighborhood. Hence, to finish our proof of continuity here, we just have to fix a point x0 and an epsilon greater than 0. And now for this given epsilon, we choose an index n that is large enough. More concretely, 2 to the power minus n should be smaller than epsilon third. And why this number helps you will see soon, but first let's go to our step function fn. Indeed, we know that fn of x0 is given by k over 2 to the power n. And that's also helpful to sketch it. We have the value corresponding to k, and the 1 corresponding to k plus 1, and the 1 to k minus 1. And now, for example, our x0 could lie here. But this also means that we can define an open neighborhood of x0 just by putting two steps together. So let's call this open set V with index k. And this one should be defined by the lower level minus the upper level. So more precisely, the lower level is corresponding to k minus 1, and let's take the open set, so not the closure. And now by subtracting the upper level corresponding to k plus 1, so there we have the closure, we actually get an open set. This is easy to see because you could write this difference as an intersection with the complement. And since the complement is open, you have the intersection of two open sets, and by the topology definition, this is always an open set. So this is the whole idea. For a given x0, we can always find the corresponding value on the step function and define this open neighborhood. And now we just have to show that the changes that can happen on this open neighborhood are small enough such that we still map into our epsilon neighborhood. So let's take an arbitrary x from the neighborhood and let's see what the calculation shows for the difference. Indeed, what we want is that f of x minus f of x0 is smaller than epsilon. And there, as you might already expect it, we can use a triangle inequality. So you see, we can just put two things in the middle and then we get three terms. So first we put fn of x in and then fn of x0. Hence, for the first and the third term, we already know that we are bounded by 2 to the power minus n. Hence, the only question is, what can we say about the difference of the step function at the point x and at the point x0? But of course, this one we also know, as you can see in the picture, it's simply the step size of the step function. So it's actually also just 1 over 2 to the power n. And there you should recognize this is exactly the reason we chose epsilon third before. Hence the whole thing is less than epsilon, which implies that we definitely map into our epsilon neighborhood. So we have continuity at every point x0, which tells us that the whole function f is a continuous one. And this was the only part that was missing, which means the proof of Urysohn's lemma is done. So this was a long video, but it was needed such that we can use this nice result from now on. And indeed, how we can use it, you will see in the next videos. So I wish you a nice day and bye bye.